Looking at the test 6C practice test, answer key. First question says, an assignment of probabilities must obey which of the following? So we know about probabilities that any individual probability has to be between 0 and 1, and that if you add up all the probabilities in the entire sample space, you have to get exactly 1, because you can't have more than 100% of something happening. So A and B are definitely true. If we look at C, it says the probability of an event is the sum of the outcomes in the sample space that make up the event. And if you just imagine a Venn diagram, if you had multiple pieces that were overlapping, for example, I'll go down to question 7. The way I've drawn this circle, if this has 0.4 in A and at 0.1, this section is also in A, then the total probability in A is 0.5. So for number 1, A, B, and C are all true, so the answer is D, all of the above. For number 2, it says event A occurs with probability 0.2 and event B occurs with probability 0.8. If A and B are disjoint, which means mutually exclusive, then what? So disjoint means that they don't overlap at all, so I drew 2 separate circles for my Venn diagram. So the probability of A and B, that would be the intersection. There is no intersection, there's no overlap, so that would be 0, so A is wrong. Again, this and for C, there's no overlap, so it can't be that. Or means you add the 2 probabilities. 0.2 plus 0.8 is 1, that's why it's B. 0.2 plus D is basically trying to trick you by multiplying 0.2 times 0.8, but you don't multiply probabilities when it's or, you add them. So number 2 is B. Number 3 says a fair coin is tossed 4 times, and each time the coin lands head up. If the coin is then tossed 1996 more times, how many heads are most likely to appear for this additional 1996 tosses? You know a coin has 2 outcomes, so it's 50-50 chance. You take 50% of 1996 and you get 998. The answer is B. Number 4, a die is loaded so that the number 6 comes up 3 times as often as any other number. What is the probability of rolling a 1 or a 6? So I drew a little table here. All the possible outcomes are 1, 2, 3, 4, 5, 6. The odds of them happening, well, 6 comes up 3 times as often, so I called it 3x. Called all the other numbers x. If you sum that up, you get 8 x's. So that means your denominator for each of these odds needs to be 8. So 1 through 5 each have 1 over 8 odds of being rolled, and 6 has 3 over 8 odds of being rolled. So you can see 3/8 is 3 times as big as 1/8. And then you're going to, they ask you, what is the probability of rolling a 1 or a 6? So we're adding the probabilities of 1, which is 1/8, and 6, which is 3/8. You add them, you get 4/8, which is 1/2 C when you reduce it. Question 5 and 6 relate to the following scenario. In a particular game, a fair die is tossed. If the number of spots showing is either 4 or 5, you win $1. If the number of spots showing is 6, you win $4. And if the number of spots showing is 1, 2, or 3, you win nothing. You are going to play the game twice. So again, I did my possible outcomes and the possible winnings. Made that table. Question 5 says the probability that you win $4 both times. So winning $4 means that we rolled a 6. The odds of rolling a 6 on a fair die are just 1 out of 6. When you're rolling the die twice, because these are independent rolls, the first roll doesn't affect the other one. All you're doing is doing 1/6 times another 1/6, or you could just square it. You get 1 over 36. The answer is C. Question 6, the probability that you win at least $1 both times. So winning at least $1 means you could roll a 4 or a 5 or a 6. So the probability of rolling a 4 or a 5 or a 6, that's half of the die. So that's 1/2, and you're doing it 2 times. Squaring it, 1/2 squared gives you 1/4. Answer is D for number 6. Questions 7 and 8 relate to the following scenario. It says an event A will occur with probability 0.5 and an event B will occur with probability 0.6. Just thinking about that right initially, 0.5 plus 0.6 is more than 1, so there has to be some overlap somewhere in here, and it says the probability that both A and B will occur is 0.1. So the overlap when you draw your Venn diagram is 0.1. So I have A and B, overlap is 0.1. The total circle A has to add up to 0.5, so that means this piece has to be 0.4. 0.4 and 0.1 make 0.5. And the total of B is 0.6. So if we have 0.1, this number over here has to be 0.5. So question 7 says the conditional probability of A given B. So the probability of A given B is the probability of B intersect A, or B and A happening, which is the overlap, divided by the probability of B. The overlap, the and, the middle is 0.1. The probability of B happening, the total over here, 0.1 and 0.5 makes 0.6. I know that might not look like a 6, but that's a 6. 0.1 over 0.6 is just 1/6. So the answer to 7 is D. Number 8. You can conclude from this scenario, are they independent? Well, we could go through and prove whether or not they are, but that would be a lot of work. If they're disjoint, disjoint means they don't have overlap at all. Clearly they overlap. Are they complementary? I don't know, we haven't talked about that. C says either A or B always occurs. So you know the probability of any scenario, the total sum has to add up to 1. If you add up each of these pieces, 0.4, 0.1, 0.5, you get the number 1. So there's nothing else that could happen. Either A happens or B happens. There's no event C. Nothing else could possibly happen in this scenario. So it has to be C for number 8. Number 9, experience has shown that a certain lie detector will show a positive reading, which means that it indicates a lie 10% of the time when a person is telling the truth. And it will indicate a lie. It'll show a positive reading 95% of the time when the person is actually lying. Suppose that a random sample of 5 suspects is subjected to a lie detector test regarding a recent one-person crime. Then the probability of observing no positive reading, if all suspects plead innocent and are telling the truth, is what? So I made up a table here to find, based off what it was given, it says the probability of positive reading, given that they were telling the truth, is 0.1. That's from the 10%. The probability of it being positive when they were lying, that's another value that was given from the problem, is 95%, so 0.95. So then I thought about, okay, what if they're telling the truth? If it's 10%, if it shows positive, then how often does it show negative? So that would be 0.9, because 0.1 and 0.9 have to add to 1. And if they're lying, it'll show positive 95% of the time, and it'll show negative then 5% of the time. So they want to know the probability of observing no positive reading if they are telling the truth. So no positive reading means a negative reading. A negative reading when they're telling the truth is 0.9. And if there's 5 suspects, you're going to do 0.9 to the 5th. When you put that in your calculator, you get this value, which means the answer is D, 0.591. Number 10, if you buy 1 ticket in the provincial lottery, then the probability that you will win a prize is 0.11. If you buy 1 ticket each month for 5 months, what is the probability that you will win at least 1 prize? So whenever you see at least 1 of something, the way you set that problem up is you do 1 minus the probability that you don't win anything. So if the probability of winning a prize is 0.11, the probability of not winning is 0.89. You're doing this for 5 months, so 0.89 to the 5th gives you 0.5584. You do 1 minus that, you get 0.4415. Rounded to 2 decimal places, that's going to give you C, 0.44. Okay, moving on to free response section. Number 11 says many fire stations handle emergency calls for medical assistance, as well as those requesting firefighting equipment. A particular station says that the probability that an incoming call is for medical assistance is 0.85. This can be expressed as the probability that the call is for medical assistance equals 0.85. Part A, give a relative frequency interpretation of the problem. So basically, relative frequency means what's going to happen in the long run. So you can just say about 85% of a large amount of calls will be for medical assistance. We know exactly, out of all possible calls, it's going to be exactly 0.85. But if you just took some large amount, approximately 85% would be for medical assistance. Part B, what's the probability that a call is not for medical assistance? Well, if it's for medical assistance, 0.85. 1 minus that would be 0.15. Part C, assuming that successive calls are independent of one another, calculate the probability that 2 successive calls will both be for medical assistance. So again, you're just doing 0.85 times another 0.85, and you get 0.7225. Part D, still assuming independence, calculate the probability that for 2 successive calls, the first is for medical assistance and the second is not for medical assistance. So medical assistance 0.85 times the second one 0.15 gives you 0.1275. Part E, still assuming independence, calculate the probability that exactly one of the next 2 calls will be for medical assistance. So this is like looking at Part D again. This was medical, not medical. Another scenario you could have was, if you flip the order, you could have a not medical and then a medical call. But either way, you're going to get the same answer. So there's 2 possible scenarios for getting this answer. So I did 2 times that number, and you get 0.2550. Part F, do you think it is reasonable to assume that the requests made in successive calls are independent? Explain briefly, because we are assuming independence the entire problem, but is that actually likely in real life? So I said it's probably not true that they're independent, because if there's some medical emergency, there's probably multiple people, like the witnesses, who could call in and report the same incident. So, for example, if someone's house was on fire, all the neighbors that are around them might call into the fire department and report the fire. And they would all be calling at the same time. And so those calls aren't independent because they're all based off the same incident. Question 12. Approximately 30% of the calls to an airline reservation phone line result in a reservation being made. So we have 0.3 means a reservation, and there's 0.7 not making a reservation. Part A, suppose that an operator handles 10 calls. What is the probability that none of the 10 results in a reservation? So no reservation is 0.7. There's 10 calls, 0.7 to the 10th power gives you 0.0282. Part B, what assumption did you make in order to calculate that probability? The assumption you make is that each of the calls is independent, and that allows you to just multiply 0.7 times itself for each number of calls. Part C, what is the probability that at least one call results in a reservation? So again, we're doing, for the probability of at least one is 1 minus the probability of no reservations over the 10 calls. We already figured that probability out in Part A, so we're just doing 1 minus 0.0282, which gives us 0.9718. Question 13. May has applied to both Harvard and the University of Florida. She thinks that the probability that Harvard will admit her is 0.4 and the probability that Florida will admit her is 0.5. The probability that both will admit her is 0.2. Make a Venn diagram with the probabilities given marked. So I have a Harvard circle, Florida circle, both is 0.2. The total for Harvard is 0.4. So if this is 0.2, this is also 0.2. For Florida is 0.5, so if this is 0.2, this has to be 0.3. Which means that if you add these up, what's the probability that neither university admits her? This added up, all these is 0.7, so the probability that she doesn't get into either college, left over 1 minus 0.7, will give you 0.3. Part C, what's the probability that she gets into Florida but not Harvard? So we're looking for the part of the circle that's Florida that doesn't touch the Harvard circle at all, which is 0.3. We're going to do question 14 in another video because I'm about to run out of recording time on this video.